Swayam Prabha. Digital India. Educated India.
It's called dimension reduction. One of the basic tools for dimension reduction is called principal component analysis, PCA. This is a very good technique, and this technique is needed because of the following. We are in a stage where we are collecting large volumes of data. I am now considering data in large dimensional space, and if the dimensionality of the vector becomes large, the processing time is also going to be large. So the question is this: is there a way to reduce the dimension of the representation of the data without losing too much of information? So you can think of it as a kind of a compression scheme. We talk about text compression, image compression. There are two kinds of compression. One is lossless compression, another is lossy compression. When I am trying to compress the text, it should be lossless compression. There are very many tools for doing lossless compression. There is a coding technique called Huffman code, which is a very, very good method for compressing text in English, likewise in any other language. If I have images, images have lots of redundancy. Image compression, we can afford to lose some information, so I can apply lossy compression to images and being able to compress large images to a smaller image. So PCA is a class of techniques that provides us tools for implementing compression with some loss. So I would like to be able to control that loss. So the technique of PCA in principle, from an application perspective, can be thought of as a method for compression, a method of shortening the representations of objects without losing too much of the essential information. So how to preserve essential information and how to throw out what you think is noise. This ability to separate the signal from the noise is what we are going to be talking about. So there are two types of approaches. One is called population-based PCA, another is called sample-based PCA. In the population-based PCA, I am going to assume X is a random variable, and I am going to talk about the properties of random variable as I exercise in probability theory. PCA, the sampled version, there it becomes statistical. I don't know the actual distributions. I only have samples. So using samples, I have to implement. So there are two facets to PCA. One is population-based PCA, another sample-based PCA. So to get the basic ideas straightened out, I'm going to be now talking about population-based PCA. So that's called the basic setup. It has to be a random vector of size m. I say this random vector is in L2. is a very technical term. A function is said to be in L2 if the square of the integral is finite. So 2 represents a square. L2 means the total energy in the function is finite. In the case of random variable, to say it is in L2 is to be able to say that its variance covariance matrix are finite. So if x is a random variable in Rm, if I say is a vector in L2, that means the random variable x is well defined, it is a finite mean and a finite each component has a finite variance, and the covariance matrix has elements which are finite. That's essentially, in principle, what L2 practically means. So without loss of generality, I am going to assume x is centered. In the previous module on Gaussian distribution, we have already talked about centering and scaling. A random variable may have a non-zero mean and a non-zero variance, will always have a non-zero variance. If you call a random variable and the variance is 0, is no more random, is deterministic. So, sometimes mean is a nuisance. I have to subtract the mean in many calculations. So, to start with, I can assume I have a data where I have subtracted the mean. If I have subtracted the mean means what? I have centered the data. I have a set of data that is already centered. So that means E of x is 0, the covariance of x is sigma, and this is the reason why I did the Gaussian distribution, to be able to give you a very good understanding of mean, centering, scaling, covariance, variance, computation of all the moments. So based on the experience with Gaussian distribution, you should be able to now visualize what's going on in here. I also want to assume, without loss of generality, to start with, my sigma is SPD. SPD means symmetric positive definite. So I have a random vector which is centered and which is a positive definite, symmetric positive definite covariance matrix. Please understand, I am not assuming x is normal. I am only assuming first two moments. That's why we are calling it is in L2. So to say a variable is in L2 is to say that I do know the behavior of the first moment, second moment, and they are finite. PCA and eigenanalysis are intimately associated with each other. Sigma is the covariance matrix, which is SPD. Now I am going to talk about, I am going to rely on the spectral decomposition, which is also called eigen decomposition. So lambda I vi be the eigen value, eigen vector. That's called eigen pair of sigma. That means sigma vi is equal to vi lambda I for I is equal to 1 tm. Now I can define a matrix V whose columns are v1, v2, vm. So this matrix V, we have already seen, must be orthogonal matrix. That means V transpose V must be IM. This matrix V is called matrix of eigenvectors. So this essentially implies that the eigenvectors are normalized. Eigenvectors are also orthogonal. This system of orthogonal vectors which are normalized is called orthonormal system. We already have seen that. Lambda is a matrix of a diagonal matrix of eigenvalues lambda 1, lambda 2, lambda m. I am going to assume lambda 1, lambda 2, lambda m is strictly ordered. Lambda 1 is greater than lambda 2, greater than lambda 3, and lambda m is the last one, minimum 1, and the minimum eigenvalue is also positive. So I can express my relation as sigma v is equal to v lambda, which we have already seen. Therefore, sigma is equal to v lambda v transpose. V sigma v transpose is lambda. So I can express sigma in terms of v and lambda. I can express lambda in terms of sigma and v. Both the relations are simultaneously true. That's the contents of the equation 4. We have already seen this a couple of different times in the earlier modules. Now I am going to, when x is a random vector, there are two quantities. I already talked about the early part of today's lecture. I can talk about the covariance matrix of x. I can also talk about the total variance of x. The total variance is equal to the sum of the variance of the components. So, variance of a scalar random variable, covariance of a random vector, and the total variance of a random vector. The total variance of a random vector is equal to sum of the variances of the m components xi. Now, xi's are already centered, therefore, the variance of xi is expected value of xi square. Xi square summation, please understand, there are two operators now, summation and expectation. Summation and expectation, they commute. The sum of the expectation is the expectation of the sum. Therefore, it is the expectation of the sum of the squares, which can be expressed as x transpose x. So, expected value of x transpose x. Expected value of x transpose x, I want to understand what it is. So, expected value of x transpose x is a scalar. Trace of a scalar is itself, you already should know that. Trace is an operation on matrices. And x transpose x is a scalar, so there are two operators involved in here. I am going to replace x transpose x by trace of x transpose. Please understand here there is a nice thing that's going on in here. X transpose x is equal to trace of x transpose x. Trace of x transpose x is equal to, I can rotate it. Trace of AB is trace of BA. Therefore, trace of x transpose x is trace of x transpose. Of course, expected value comes out because trace and expectations, they commute. So, expected value of the trace is equal to trace of the expected value. The expected value of x transpose is sigma. And from the previous slide, that is equal to trace of V lambda V transpose. Again, trace of ABC is trace of BCA, trace of CAB, we have already seen that. That becomes equal to trace of V transpose V sigma. V transpose V is identity. Therefore, that becomes equal to trace of sigma. Trace of sigma is essentially the sum of the, okay, here the sigma must be lambda. I'm sorry. The sigma in here must be lambda, so this must be sigma must be lambda. The trace of lambda is simply summation of lambda I. Sir, there is a symbol of matrana mathamadima. Huh? Mathamadimilla? Okay, good. I will let you know what to do. Thank you. So, the sum of the variance of the components of x is equal to sum of the eigenvalues of the covariance matrix. So, that is the result. So, in this case, I have to replace this sigma by lambda, this sigma by lambda, that becomes summation of lambda I. Now, I am going to be talking about the statement of a particular problem of interest in PCA. Find a set of m deterministic orthonormal vectors, xi1, xi2, xi3, xim, where each of the vectors xi is in Rm, and a set of m non-uncorrelated random coefficients alpha 1, alpha 2, alpha 3, alpha m, such that I am going to express x as a linear combination of alpha 1, xi1, alpha 2, xi2, alpha m, xim. Look at this now. It's a very interesting problem. X is a random vector. Xi's are the vectors. I want to be able to express x as a linear combination of a set of orthonormal vectors. Orthonormal vectors means the inner product of any two is 0, the length of each vector is 1, Xi's are given deterministic quantities, X is random. So Xi's are deterministic, X is random. So the only way I can make X random by making the coefficients alpha 1, alpha 2, alpha m to be random. So in 7, by picking alpha 1, alpha 2, alpha 3 are random coefficients, I get a linear combination with random coefficients, I am able to express X. And then I am also putting another constraint, the variance, the total variance of the components of AI Xi. Please understand, Xi is a vector, that is a fixed deterministic quantity, alpha I is a random quantity. I would like to be able to compute, so this is scalar times a vector. I would like to be able to compute the total variance of this vector, which is alpha I Xi to be lambda I. I hope you understand the design problem now. X is a random variable that is given to you. I would like to be able to express X in terms of a linear combination where the vectors that participate in the linear combinations are deterministic. I want the coefficients to be random. Such a set of orthonormal vectors are called principal patterns. The associated random coefficients are principal component. So I am now trying to give you the pure definition, a mathematical definition of what principal patterns and principal components are. So the principal patterns are a set of orthonormal vectors. The principal components are a collection of random variables. I am going to take a linear combination of the principal pattern with the principal component to be able to synthesize, to be able to verify, to be able to build a random variable X. Not only that, I would like to be able to control. We already see the total variance of X is lambda 1, lambda 2, the sum of all the lambdas. I would like the total variance of the first component to be lambda 1, second component to be lambda 2, mth component to be lambda n. So I would like to be able to preserve the properties of X, but I would like to be able to decompose X in this particular form. So expressing X in this particular form is called expressing X in the principal patterns and principal component. This is the starting theory of principal component, the starting point of it. Now I am going to introduce another quantity called Rayleigh coefficient and its properties. Again, you can see matrices and statistics are intertwined. So I am going to introduce another matrix, a quantity from matrix theory called Rayleigh coefficient. Let A be an SPD matrix. Let eta be a vector, all sizes m. Given A, define a functional, and we have already talked about a functional is a mapping from a vector space to the real line. So eta is a vector, Rm is a vector space, A is a fixed matrix, or subscript A of eta is a function that maps Rm to R. So it's a functional that depends on the matrix A. How do I define the functional? The functional R subscript A of eta is defined by the ratio of the quadratic form of eta with A divided by the inner product of eta with eta, that is given by the equation 9. We already so let mu and xi be an eigenpair of A. Please remember, we have already talked about the eigenpair of sigma in the previous cases. Now I am going to introduce a new concept. To introduce this new concept, I am using a matrix A. I am trying to compute the eigenvalues and eigenvectors of that. The eigenvalues or eigenvectors of A are going to be called mu and xi. So what is the property of this eigenvalue eigenvectors? A of xi must be equal to mu. So RA of xi is equal to xi transpose A eta divided by E transpose eta, that is equal to mu. Why is that? Please go back. A xi is mu xi. So if you substitute A xi is mu xi, the numerator becomes mu times xi transpose xi. This is xi transpose xi. They get cancelled. You get mu. Since the eigenvectors are normalized, xi transpose xi is 1. So you can really see RA xi is xi transpose A xi is equal to mu. I hope you are all with me now. That means a Rayleigh coefficient as defined by 9, when you apply that to the eigenvalue eigenvector pair, the value of the Rayleigh coefficient coincides with the eigenvalue. That's the equation 9. So I would like to emphasize some of the things. I would like to be able to define a new functional called Rayleigh coefficient. I defined the Rayleigh coefficient in general form in 9. Now I am going to talk about a specific type of Rayleigh coefficient with respect to the vectors, which are eigenvectors and eigenvalues. So mu xi be the eigenvalue, eigenvector of A. So the Rayleigh coefficient of A with respect to its own eigenvalue is equal to mu. So the Rayleigh coefficient, you can think of it, extracts the eigenvalue of a given matrix. So 9, 10 and 11 essentially tells the relation between the concept of Rayleigh coefficient as a functional and the specific property of the Rayleigh coefficient when you chose eta to be, eta is any vector. If you chose any vector to be the eigenvector of A, I get the constant mu. So now I would like to be able to set my matrix A is equal to sigma. Recall that Vi are the normalized eigenvectors corresponding to eigenvalue lambda I of the covariance matrix sigma. I want to be able to ultimately study sigma. I want to introduce a new concept called Rayleigh coefficient. So I introduce the Rayleigh coefficient in the context of the matrix A, general vector eta, and the specific eigenvector of A. So that's a general concept and property of Rayleigh coefficient. Now I would like to specialize by picking A to be not any A but my value, but by matrix sigma. What is sigma? Sigma is the covariance matrix of my random vector x. And what is the random vector x I am started with? X is a centered random variable, its mean is 0, its variance is sigma. And we know x is in L2. So I know I may not know the exact distribution of x, but I do know the mean and its covariance. So from level, if I substitute A is equal to sigma, if I substitute xi is equal to Vi, you can readily see or substitute sigma Vi is Vi transpose sigma Vi, that is equal to lambda I, that comes from the spectral decomposition or the eigen decomposition of sigma. So in view of the ordering of the eigenvalues, if the value of the Rayleigh coefficient evaluated Vi is lambda I should have Rayleigh coefficient at V1 is greater than Rayleigh coefficient at V2 is greater than Rayleigh coefficient at Vn. So 13 is a direct consequence, which is the combination of the definition of the Rayleigh coefficient and the ordering of the eigenvalues. Now I am going to consider a linear functional of x. Please understand, I have a design problem. I want to be able to design. I want to be able to express x using principal patterns and principal components, and that's what I am working towards. So consider the eigenvalue, eigenpair lambda I Vi of sigma. Sigma Vi is Vi lambda I. This is equal to Vi transpose Vi is equal to 1. We already know that because they are orthonormal system. Here comes the connection between the principal pattern, the design problem, and the Rayleigh coefficient and the properties. Now I am going to define a new random variable. Please understand, sigma is a matrix, is a given matrix. There is nothing random about sigma. I know its eigenvalues and eigenvectors. X is random, Vi is not random. I can compute the inner product of Vi with Xi. Since X is random, alpha is random. So alpha i's are the random scalar expressed by the inner product of Vi with respect to Xi. Now please understand, Vi transpose X is the linear function. Multiplying a vector X by Vi transpose makes it a linear functional. So this alpha I is essentially a linear function of Xi with respect to the eigenvector Vi. So alpha I is a linear function of the given random variable X. Now please understand, our goal is to be able to express X in terms of alpha I and xi I. So I have now beginning to give you an impression about where alpha i's are coming from. So the mean of alpha I is mean of Vi transpose X is equal to Vi transpose E of X that is 0. That means this random coefficient alpha is random because X is random. X is the mean 0. Alpha is a linear function of X. So alpha I has a mean 0. If I want to be able to compute the variance of alpha I, because it is mean 0, it is essentially E of alpha I square. But alpha I is Vi transpose X Di. So that's the definition of alpha I square. This I can, inner product has a property A transpose B is B transpose A. So by applying that, you can readily see this is equal to Vi transpose X transpose Vi, X transpose X times Vi. Expected value of X transpose X is sigma. So this is simply Vi transpose sigma Vi. And that's a Rayleigh coefficient, which we already know is lambda I. Wow, you must be having an aha moment now. So by combining the eigendecomposition of the covariance metric sigma of the random variable X and defining a linear functional of X using the eigenvectors, I define alpha I, and alpha I are such that their mean 0, their variance is equal to lambda I. What is lambda I? The eigenvalues of sigma. So now I am going to talk about the properties of the eigenvector alpha I Vi. Vi's are not random, alpha I is random. I hope you are with me now. So expected value of alpha I Vi is equal to alpha I is Vi transpose X times Vi. If I simplify this, Vi transpose X, we have already seen that. That's alpha I. Expected value of alpha I is 0. So this vector has a mean 0. Let's assume this vector Vi has m components, h1, h2, hm. We already know Vi transpose Vi is 1. So I'm simply trying to express the elements of the vector Vi to be h1, h2, hm. We already know it is normal. Therefore, alpha I Vi is equal to alpha I Hj summation 1 to m. So the variance of alpha I Vi is equal to sum of the variances. This is the vector, the sum of the variance of the components of that. So variance of alpha I Hj, j running from 1 to m summation. Hj's are constants. So if you multiply a variable by a constant, the variance gets multiplied by the square. So the Hj square variance of alpha I. You already know the variance of alpha I is lambda I. So this is simply summation of Hj square. But Vi transpose Vi is equal to 1 essentially means summation of Hi square is all equal to 1 because it's a unit vector. So this is lambda I. So we have done several things now. Alpha I is a random variable means 0. Alpha I is a random variable is the variance of lambda I. Alpha I Vi is a random vector whose mean is 0. The total variance of the random vector alpha I Vi is also lambda I. Doesn't it? So there are lots of quantities involved in here. So what is the correlation between alpha I and alpha j? I hope you understand. Alpha I and alpha are defined by, let's go back to the definition of alpha I and alpha j. In equation 14, alpha I is defined by Vi transpose x. What is alpha j? Vj transpose x. What is Vi, Vj? The two orthonormal eigenvectors of the symmetric positive definite matrix, the covariance matrix, sigma. Therefore, the covariance of alpha I, alpha j, because they are mean zero, is simply the product of Ei, alpha I, expected value of alpha I, alpha j. I substitute for alpha I, I substitute for alpha j. Vi transpose Vj comes out. Vi transpose Vj comes out. So this is sigma. Now think about this now. V transpose sigma V is lambda. So V is the, if you consider the matrix V, sigma V transpose V is lambda. Lambda is a diagonal matrix. The off-diagonal entries are 0. So if I is not equal to j, this product is 0. That comes from the property of eigendecomposition. So 19 essentially tells you alpha I and alpha j are uncorrelated. Why this is true? That is because V transpose sigma V is diagonal matrix. In a diagonal matrix, off-diagonal elements are 0. So this is 0. That means alpha I and alpha j are uncorrelated for I not equal to j. So solution to the problem stated above. What is the set? What is the solution? What is the problem? I am given a random vector x. I would like to be able to find m principal directions xi1, xi2, xim, and m random coefficient alpha 1, alpha 2, alpha m, such that x is equal to alpha 1 xi1 plus alpha 2 xi2 plus alpha m xim. The whole question was, how do you pick the xi? How do you pick the alpha? Answer is coming from the previous analysis. By setting xi I is equal to Vi. What is Vi? Vi's are the eigenvectors of sigma. We first identify the required set of m orthonormal or orthonormal eigenvectors to be the principal directions. So you remember, xi1, xi2, xim are required to be the principal directions. The principal directions, I want them to be linearly independent. If I assign xi I is equal to Vi, Vi is an orthonormal. Orthonormal vectors are trivially linearly independent. Therefore, the principal directions I require for the representation to solve the problem are simply given by the m eigenvectors of sigma. Now, by setting alpha I is equal to Vi transpose x in 7, we identify the required set of uncorrelated random coefficients such that the variance of Vi transpose x is equal to lambda I. This gives you the solution to the problem we posed. Indeed, the required expansion for x is given by, look at that, x is equal to V1 transpose x times V1, V2 transpose x by V2, Vm transpose x by Vm. Wow, this is a very fundamental result. So what is it we are saying? If x is a random vector with mean 0 and covariance sigma, x admits a unique representation as a sum given in 20. So this is what's called decomposition of a random vector using principal patterns and principal coefficients or principal component. The principal components are alpha 1, alpha 2, alpha m. The principal patterns are V1, V2, Vm. So you can readily see the representation of the random variable can be derived from the eigenvalues and eigenvectors of its covariance, and by suitably defining linear functional with respect to the linear function of x with respect to the eigendirections. So expression 20 provides you the answer to the problem we are talking about. Now, projection matrix along the eigenvector of sigma. So eigenvector sigma is a matrix. There are n eigendirections. Eigendirection is a direction that is fixed, which is the characteristic property of the covariance matrix. It's a vector in the n-dimensional space. If I have a vector in the n-dimensional space, I should be able to project any point onto that space. We have already seen projection matrices when we talked about least squares. That's the reason we talked about modeling least squares at great length. We talked about orthogonal projection matrix PH. So given a vector H, what is the orthogonal projection matrix that will project points outside of H onto H along the direction H? And that projection matrix is given by PH is equal to H times H transpose H inverse H transpose. This is the result that comes from modeling in least squares theory, linear least squares theory. So, given a matrix H, if I want to be able to project objects onto that space, the orthogonal projection matrix has an expression given by 20. That's for a general definition, for a general direction H. Now, I have already seen the principal directions or the principal patterns are given by the eigendirections. Now, I would like to be able to project objects in the m-dimensional space onto the eigendirection. I want to have a projection matrix to project objects onto that eigendirection. So that is given by replacing H by V. PV is equal to V transpose V inverse V. But V transpose V, the V's are unit vectors, they are orthogonal. So the length is 1, so VV transpose. VV transpose is a m by m matrix, is an outer product matrix, rank 1 outer product matrix. So this PV, which is given by VV transpose, is the orthogonal projection matrix along the direction V. So, if I have a vector x, if I have an orthogonal, if I have an eigenvector V, now please understand, V is the eigenvector of sigma, and sigma is the covariance of x. Sigma and x are different, so x and V are different. So x is a vector in arm space, V is a vector in arm space. I would like to be able to project the vector x onto onto along the direction V. So that's equal to V transpose x is equal to V times V transpose x is also equal to V transpose x times V. Please understand, V transpose x is a scalar. I can multiply a vector by a scalar either on the left or on the right. With me? So, equation 23 is a simple expression for the projection of x along V. Consequently, each of the m terms in the summons on the right hand side of 20, let's look at this now, 20. Look at that, each of the right. So what is this? This is the projection of x along V1, projection of x along V2, projection of x along Vm. So each of the terms in 20 has the same form as the projection in 23. I hope you are all with me now. Therefore, consequently, each of the m terms in the summons on the right hand side of 20 is a vector resulting from the orthogonal projection of x along the m orthogonal basis for Rm, which are eigenvectors of sigma. That means the expression 20 is simply an alternate expression that expresses x not in terms of the original coordinate system, but with respect to the new coordinate system defined by the n orthonormal eigenvectors of the covariance sigma. So, equivalent representation of points in Rm. Equivalent representation of point in Rm. So, a random vector xr belonging to Rm denotes a point in Rm which has a standard orthogonal basis with Ei. Ei is a standard orthogonal basis. So, this is a standard representation. That means a random vector is expressed as a linear combination of the product of random variable multiplying a deterministic vector. Ei's are deterministic, xi's are random. Ei's are the ith unit vector. So that's one representation, the standard basis. The new orthogonal bases are formed by the principal patterns. The principal patterns are the principal directions, which are the eigenvectors of the covariance matrix of X. So, in the same point X now can be expressed as alpha I Vi, where alpha i's are X transpose Vi. Alpha I are X transpose Vi. That's the same point in Rm admits two labels X. So, X is the coordinate of the random vector in the original coordinate system. Alpha 1, alpha 2, alpha m are the coordinate of the point X in the new coordinate system. So, the vector alpha represents the same point as the vector X. Are you with? So, these are the two equivalent representations. So, alpha are called the principal component. So, what are the principal component? Principal component of X are simply the coordinates of X with respect to the new orthonormal coordinate system defined by the orthonormal vectors of the covariance matrix sigma. So, what is alpha? Alpha is alpha 1, alpha 2, alpha m, V1 transpose V2 transpose Vm transpose times X. So, this is the matrix V transpose times X. So, alpha is essentially V transpose X. So, this is called the principal component. Alpha is obtained by the linear transformation V transpose of X. V is the matrix, V transpose is the matrix, multiplying a vector by a matrix is the linear transformation. So, the principal component of X is obtained by a linear transformation of the given random vector X itself. Conversely, V transpose is V inverse. Orthogonal matrices, transpose is the inverse is the transpose. Therefore, from X I can go to alpha, from alpha I can go to X. So, alpha is equal to V transpose X. That tells you X is equal to V alpha. X is equal to V alpha. In this representation, what is that we know? The variance of X is equal to variance of alpha. That means the principal component is such that its total variance is preserved. Additionally, I have variance of alpha 1 is greater than variance of alpha 2 is greater than variance of alpha m, which is strictly 0. That means now I am able to express X in the new basis given by the principal patterns whose coefficients are the principal component. The property of the principal component is such that it has an added property, namely the variance of the principal components are steadily decreasing as I go from alpha 1 to alpha m. This is the additional property that that comes from this analysis. So, X is random, alpha is random, there are two random vectors. I would like to be able to compute the covariance between the two. So, what is the topic now? Covariance of X and alpha. Covariance of X and alpha. Components of X are uncorrelated with those of alpha. Components of X are correlated. So, please understand, the components of X is correlated. Why is that? The correlation, the covariance matrix of X is sigma. Sigma in general is not diagonal. If sigma is not diagonal, the components of X are correlated. But we have already shown alpha I and alpha j are not correlated. So, the same point has two representations, one whose components are correlated, two alpha whose components are uncorrelated. Therefore, if X's are correlated among themselves, alphas are not correlated among themselves. So the covariance of X comma alpha is equal to covariance of X times alpha transpose. Why? The mean of X is 0, mean of alpha is 0. So the general definition of covariance is E of X alpha transpose minus E of alpha transpose. E of X and E of alpha transpose are 0. E of X is 0. Alpha transpose is X transpose V. So E of X transpose X is times V, the sigma times V. I hope you're all with me now. And sigma is equal to V sigma V trans. This is X transpose X. E of X transpose X is sigma. V comes out. So then sigma V. So V lambda V transpose V times V. V transpose times V is identity. So this will become V lambda. So the correlation between Xi and Vi is that sigma ij, well, let me call it sigma ij, correlation between Xi alpha j, which is equal to covariance between Xi alpha j divided by variance of Xi, variance of alpha j, the product, square root of that, with me? So I'm computing the covariance between the ith component and jth component of X and alpha, which by definition is given by the right hand side. From 29, the covariance is V sigma ij, that is equal to Vij lambda j. The variance of alpha j is lambda j from 16. Hence, the covariance between Xi and alpha j is square root of lambda j Vij divided by variance of Xi to the power half. That means the standard deviation of Xi. So this essentially comes from the definition. And what is the interpretation of sigma ij? The summation of sigma ij square, I am going to substitute for each of sigma ij from the previous one. So the bottom is the denominator of variance of Xi. So lambda j Vj square, Vij square, summation is over j. This is equal to V lambda V transpose II divided by variance of that. V lambda V transpose is lambda I, variance of Xi is also lambda I, so that's equal to 1. Therefore, sigma ij is such that it adds up to 1. That means sigma square ij denotes the fraction of the variance of Xi explained by the principal component alpha j. Explained by the principal component alpha j. So that's an important interpretation that comes from considering the covariance of X and alpha. Alpha comes from X. X by itself, they are correlated. Alpha by themselves, they are uncorrelated. But there is correlation between the components of X and components of alpha. That's what we are trying to talk about. So the sum of the squares of sigma ij square is 1, and that gives you an apportionment of the fraction of the variance of Xi explained by the principal component alpha j. That's an important interpretation. Now I'm going to give an example quickly. Let m is 2, X is equal to n0 sigma, sigma be 1 1, rho, that means sigma 1 square is 1, sigma 2 square is 1, variance of x1 is 1, variance of x2 is 1, covariance of x1 x2 is rho. The eigenvalues of this are 1 plus rho and 1 minus rho. You can readily check. You can also compute the eigenvectors to be 1 over square root of 2, 1, 1, 1 over square root of 2, 1 minus 1. They are unit normal, orthogonal. So please check these calculations. They are very simple but educative examples. So V transpose is 1 over square root of 2, 1, 1, 1 minus 1. The principal components alpha, alpha 1 is equal to V transpose x. So this is V transpose, this is x. Therefore, alpha 1 is equal to 1 over square root of 2 x1 plus x2, alpha 2 is equal to 1 over square root of 2 x1 minus x2. So given x and its covariance, I have now computed the principal components, alpha 1, alpha 2. The variance of the principal component, the variance of alpha 1 is the variance of 1 by square root of 2 x1 plus x2, which is equal to 1 over 2, the expected value of x1 plus x2 whole square, which when you evaluate it now becomes lambda 1. Variance 1 plus rho is lambda 1, so that this is essentially another way of looking at it. So verified variance of alpha 2 is 1 minus rho is lambda 2. Using this simple example, you should be able to verify the entire theory that we have talked about. So comparison of the variance of the components of x and alpha. X is such that variance of x1 is 1, variance of x2 is also, variance of x2 is also 1. Alpha is such that variance of alpha 1 is 1 plus rho, variance of alpha is 1 minus rho. Therefore, the variance of alpha 1 is greater than variance of alpha 2 since rho is greater than 0. I am assuming they are positively correlated. Covariance between x and alpha, again from 29, I can compute the covariance between x and alpha to be V sigma, which is 1 over square root of 2 times the product of these two matrices, which is given by 1 over square root of 2, 1 plus rho, 1 plus rho, 1 minus rho, rho minus 1. The correlation sigma ij between xi and alpha j, this must be alpha j. So from 31, variance of x1 is the variance of x2 is 1, sigma 1, 1 is square root of lambda 1 v11, which is 1 plus rho divided by 2 times square root of that. Likewise, we can see the component sigma 11, sigma 12, sigma 21, sigma 22. So verify now sigma 11 square plus sigma 22 square. I'm sorry, sigma 11 square plus sigma 12 square is 1 half of 1 plus rho plus 1 minus rho, that's 1. Sigma square 21, sigma square 22 again is 1. All the theory is now verified, established. I am now going to talk about an example in a multiple dimension. In this case, x is Rm, x is normal mu and sigma, sigma is a SPD. I have an eigen decomposition. I am now going to center. I am assuming x was centered, here x is not centered, so I am subtracting the mean. I am going to transform V transpose x minus mu is alpha. Verify E of alpha is 0, variance of alpha is lambda I. The covariance of alpha I, alpha j is 0, and the variance of alpha 1, alpha 2, alpha 3, they are decreasing as it should. So it's a very simple extension of the problem. So the total variance of x is equal to the total variance of sigma, which is equal to the total variance of alpha I. The product of all the variances, I is equal to 1 Tm, is the product of all the lambda i's is equal to the product of eigenvalues is called the determinant. The sum of the eigenvalues is called the trace of the covariance matrix. So we have already talked about the mathematical aspects of what is the principal pattern, what is the principal component, and how the same vector x can be represented using principal patterns and principal components. That's the basic theory of representation in principal component analysis. Now, statistical data analysis, SDA. The goal of statistical analysis is to explain the observed spread in the variable. Let me check how many we have. Okay, we have quite a few. I don't think I'll be able to cover, but I would like to be able to state something and then continue, okay? So what is the goal of statistical data analysis, SDA? Recall, the ultimate goal of statistical data analysis is to explain the observed spread in as measured by the variance in the data. Please understand, if somebody gives you the data, you can't change the data. The data has its own spread. So data has a mean, it has a spread. I want to be able to understand the spread in the data. That's one of the ultimate goal of being able to understand the data. That's a fundamental question in statistical data analysis. The total variance of the data can be modeled as a sum or the natural or inherent variations in the signal components and the additive part that corrupts the signal. So the total variance is a measure of the variance in the signal plus that comes from the noise that is affecting the system. So, look back. So, the above analysis rests on two basic observations. The total variance given of the given random vector sigma is equal to sum of the non-negative eigenvalues of the covariance matrix sigma of the random variable. The variance of the projection of x along the eigenvector equal to associated eigenvalues, and the resulting additive decomposition of x as a linear combination of uncorrelated components in 20 is critical to the use of is critical to the principal component analysis. So that is the summary of what we have done. So in principle, we have now introduced, starting with the random vector and an associated covariance matrix, we defined an additive decomposition which defines the principal patterns and the principal components. What the advantage? The original vector x has correlated coefficient. The principal component are uncorrelated. The principal patterns are deterministic quantities. So it is simply a transformation in the vector space. By simply transforming to the new to the new space given by the eigenvectors, I am able to decorrelate the components of alpha, which is the same representation of the vector x. We have been studying the basic mathematical principles behind PCA. We have already talked about what principal patterns, principal component, and how this linear transformation converts a given random variable from the original basis to the new basis. The same point can be represented by a vector x or by the vector alpha. We talked about the variance between components of x and components of alpha. We illustrated all these by a simple example of n is equal to 2. Now we are trying to generalize that to a case when the random vector x is a m-dimensional random vector. So let x be a random vector in the m-dimensional space, and x inherits a normal distribution with the mean mu. Sigma is a covariance matrix. It is further assumed that sigma is symmetric and positive definite. Symmetric positive definite matrices admit eigenvalue, eigendecomposition, which is V lambda V transpose. We already know V, the matrix of vectors of eigenvectors of sigma. Lambda is a diagonal matrix of eigenvalues of sigma. The first column of V corresponds to the maximum value, maximum eigenvalue, second column, second maximum, and so on. We already know the principal component alpha, the vector alpha, is simply a linear transformation V transpose x. Here I have V transpose x minus mu because in the earlier development, without loss of generality, I assumed x is a mean zero value. So I am trying to first center x by subtracting mu and transforming by V transpose. We have already established E of alpha I is 0, variance of alpha I is lambda I. That's the important thing. The variance of the principal component are equal to lambda I. That means that lambda I has a very natural interpretation. The eigenvalues have a very natural interpretation of representing variances of the principal components. We also saw alpha I, alpha j, the correlation between alpha I, alpha j is 0. X has correlated components, alpha is a decorrelated version of X, and we also know that the variance of alpha 1, this must be 1, alpha 1 is greater than the variance of alpha 1, this must be alpha 1 is greater than alpha 2 is greater than or equal to alpha m, and alpha m is positive. That is because of sigma being symmetric and positive definite. Now we are going to continue in the same vein. The total variance of the component of the vector X is equal to the trace of the matrix, which is equal to the sum of the variances of alpha I. The product of the variances of alpha I is as again the product of the eigenvalues, and the product of eigenvalues is the determinant of the covariance matrix sigma. Recall that the ultimate goal of any statistical data analysis is to explain the observed spread as measured by the variance in the data. That's a fundamental thing. You can't change the data. The data inherits a very natural dispersion in the space of representation. So I would like to be able to describe this dispersion, and if I can explain the dispersion, then I can say I understand the distribution of the data. So the total variance of the data can be modeled as the sum of the natural or inherent variations of the signal component and that of the additive noise that corrupts the signal. So there are two components to this variation. One is the natural variation in the process that is being observed. Second, the variation induced due to the observation noise. The above analysis rests on two basic observations. The total variance is given by the in the given random vector X is equal to the sum of the non-negative eigenvalues of the covariance matrix sigma of X, sigma of X. So that's a fundamental discovery we have made using this analysis. And the variance of the projection of X along the eigenvector is equal to the associated eigenvalue. So if I project X along the first eigenvector of sigma, I get the maximum variance which is equal to lambda 1. The second eigenvector, the second maximum, the last eigenvector is the least eigenvalue. The resulting additive decomposition of X as a linear combination of uncorrelated components in 20, that means I am able to express X as a linear combination of the principal patterns and principal components. In this particular case, the patterns are given by the eigenvectors, the components are given by the alpha i's, and that's critical to the principal component analysis. So there is a natural partition of the variance that comes out of this discussion. Under the assumption that the eigenvalues of sigma are distinct, by ordering them in the decreasing order, it is immediate that the ith component of X, the ith component of X transpose Vi inherits a fraction lambda I divided by the sum of all the lambda i's of the total variance. Please remember, the sum of all the eigenvalues represent the total variance in the vector X. When I projected, we found out that the projection of X along the ith eigenvector has a distribution along that line. The variance of that is lambda I. So lambda I over the sum of all the lambda i's represents the fraction of the total variance explained by this projection along the ith principal direction. Now I am going to pick a small real number beta such as 0.01, 0.05, etc. So given beta, which is small, positive, I want to be able to find an integer k such that for k running from 1 to m, I am looking for the ratio summation lambda I equal to 1 to k divided by summation I is equal to 1 to m. That means the sum of the variance in the first k components divided by the sum of the variances in all the components is greater than or equal to 1 minus beta. Is greater than or equal to 1 minus beta. So if beta is 0.01, I am looking for a case such that the total variance in the first k components will be at least as large as 99% of the total variance. 99% of the total variance. Why is that? We do know variance is there are two components of the variance. One is the natural variation of x, another is the one that is induced by the observation noise. Observation noise doesn't have any signal. We want to be able to only extract the signal from signal plus noise. So there's no point in trying to carry the noise component. So I would like to be able to separate the signal from the noise. This ratio for a given beta essentially helps you to separate the signal from the noise. That's the idea here. That's the idea here. That is, the first k eigendirection corresponding to the k largest eigenvalue together inherit at least 1 minus beta times the total variance. Using these k components, now we can construct the signal component that the exercise. So what is the signal component? X hat. I am now estimating the signal from signal plus noise. So that is equal to the coefficient alpha, which is x transpose Vi, alpha I, which is Vi, I is equal to 1 to k. The rest of it, x minus x hat, is going to contain the sum of similar quantities for I running from k plus 1 to m. So the rest of it. This rest of it, as given in equation 35, is often considered as a noise component, because we do know the signal has been corrupted by noise. So you can see the role of PCA is to be able to separate the signal from the noise by doing this projection. In the event the component of x are uncorrelated, that means if the original vector x is uncorrelated, then sigma would be a diagonal matrix consisting of the eigenvalues which are the variances associated with the components itself. In this case, x has been expressed in the original basis itself. EIs are the standard ith unit vector, where there is 1 in the ith location, 0 elsewhere. Consequently, unless the condition number lambda 1 by lambda n is large, or the ratio lambda 1 minus lambda m by lambda 1 is close to 1, we may not be able to get the k mode approximation for x for small values of k. So I want you to be able to understand these are the cases where I may not be able to find a smaller value of k smaller than m. So what does it say? Either the condition number is large. So unless the condition number is large or the ratio is close to 1, we may not be able to get the k mode approximation to x for small values of k. This is called quality of approximation, and this happens, I would like to go back. This happens when, if you plot the eigenvalues, which is the index I, lambda 1, lambda 2, lambda 3, 1, 2, 3, and so on. If the eigenvalues fall very fast, you can readily see the variance, eigenvalues representing the variance, this is a lambda. The variance becomes lower and lower as the index becomes larger and larger. In this case, we may be able to cut it out. This may be the value of k. So what is left behind is that of the variance. Suppose the eigenvalues decrease like this. In this particular case, the eigenvalues don't decrease. Eigenvalues represent the variance do not decrease. So in this case, k, small k is not possible. In this case, small k is possible. These are the two distinct behavior that we need to keep at the back of our mind. This plot is the plot of the eigenvalue versus the index. So the rate at which the eigenvalues decrease is going to give you an indication that there is a strong signal component and there is a which can be extracted from the noise component. But if the eigenvalues decrease very slowly, then you do know that the variance of the signal component do not change much, and there can be more information even in the lowest eigenvalue. That is the implication of that. Now I am trying to approximate x hat is the signal, x is the original quantity. I would like to be able to quantify the quality of approximation in 34, and that can be measured by quantifying the variance of the difference in 35. So look at this now. Let me go back. 35 is the approximation. So I would like to be able to quantify the quality of this approximation, and we are going to quantify the quality of the approximation, that the error in the estimate. You can think of it x hat as an estimate. Now please remember, throughout this course we are trying to have some estimate that is the true value. The difference, we call it error residual, and we are always interested in the quality of the residual. In the least squares we are interested in the magnitude of the residual. Here we are interested in the variance of the residual. So there is a similarity between the ways of trying to quantify the quality of errors. So recall from 14 and 16 that xi, the mean of the projected random variables, which are all 0, and the variance of x transpose v is lambda I. Hence, if I am interested in computing the variance of x minus x hat, it is simply x minus x hat transpose x minus x hat. That comes from the basic definition, which is also equal to the trace of the matrix of the covariance, of the covariance defined by 37, which is the variance of the covariance matrix of the error. Substituting 35 in 37 and simplifying. So we now have a representation. So we know we have picked the first k components for x hat. X has all the components. So the difference between x and x hat has only components m minus k components running from I is equal to k plus 1 to m. So this is I running from k plus 1 to m, and its transpose. So that's a vector, that's the transpose of the vector, inner product. If you simplify this, vi's are orthogonal to each other. Therefore, the only thing that is remaining is the middle term, because vi is perpendicular to vj, orthogonal to vj. And this can be further simplified into this, and that's a variance of the I plus 1th ith component for I running from k plus 1 to m, and that's equal to lambda I. It is a summation I is equal to k plus 1 to m. So what is that? That's a very interesting result. If I throw away the last m minus k principal components when we are trying to approximate x, the amount of variance associated with that thrown away part is essentially given by the sum. And please remember, we have lambda 1 greater than or equal to lambda 2 greater than or equal to lambda k plus 1, all greater than or equal to lambda m. So this is the sum of the least m minus k eigenvalues. So the least m minus k eigenvalues has an inherent optimality associated with it, and that accounts for the variance of the error. So there is an inherent optimality. The ordering of the lambda i's from lambda 1 to lambda n, lambda 1 being the maximum, lambda n being the minimum, it is immediate that the sum of the right hand side of 38 is the sum of the least m minus k values of lambda, and hence is the minimum for every k. Hence is the minimum for every k. So what does this tell you? By looking at the plot of the variance, the lambda versus its index, by examining the rate at which lambdas decrease, we may be able to find a good lambda for a given beta. We may be able to find a good k. Sorry, it's not lambda; it's a good k for such that what is thrown out is only beta portion. Beta is very small. These topics are very standard. Principal component analysis was introduced by Pearson in 1902. Now you can see it is well over 120 years. Hotelling in 1935, he essentially resurrected the mathematical basis for the PCA as we now know today. That's called the most predictable criterion, which was published in 1935. The role of PCA, the PCA that we talked about is based on theoretical analysis of the random vector X. This is called population based analysis, because I know the basic distributional properties of X, either the first two moments or the distribution itself. But when we are given a data set, we have to compute the covariance and we have to extract the eigenstructure from the covariance. So that's called the sample counterpart. The sample counterpart of PCA is called empirical orthogonal function, UOF. Within the context of meteorological weather prediction, it was first analyzed in 1956 by Ed Lawrence, empirical orthogonal function and statistical weather prediction. There is a very nice book that deals with Storch and Zweier's statistical analysis of climate research in Cambridge University Press, 1999. This book talks about all aspects of basic statistical tools needed in climate science, in climate research and climate science. Now I would like to end the discussion with a couple of exercise problems. Consider the expression 34, which is given by this. That's the K-mode approximation. We know what each of these coefficients are. X hat can be now written as this part. I am trying to collect all the x's outside. It's a very simple exercise in matrix vectors theory. So you can essentially think of this is the matrix consisting of the first k eigenvectors, its transpose. V transpose is the full matrix. V minus ik is this can be represented by like this, and so V is RMM. Lambda is a diagonal matrix. So K is a diagonal matrix whose elements are either, the diagonal elements are either 0 or 1. It is 0. The first K elements of the diagonal are 0. The rest of the diagonals are 1. So if you subtract this matrix K from I, you are only going to get 1s along the last K plus, the last M minus K diagonal elements. The last M minus K diagonal elements. I would like you to be able to rewrite the expression to be able to verify this relation. The relation is in 40. So please verify this relation. With that, we come to the end of the discussion on the population based analysis of PCA. So this lays the foundation, the theoretical foundation. Here, the strength of the analysis depends on our assumption about the knowledge of the unknown vector X. We now know we have information about the distributional properties of X. Once you have the distributional properties, the first moment, second moment, we can derive the whole thing by combining the properties of eigenvalues and relating to the principal components. With that, we conclude this module. Thank you.